Well, if you ever watched an episode of the 1990s sitcom Friends, then you might want to know just how attracted were Ross and Rachel to one another. And we can actually use physics to answer that question. Here are the quantities we'll need to know. If we refer to Ross as object number 1 and Rachel as object number 2, we need to know both of their masses. So I'm going to make some estimates here and say the mass of Ross, object number 1, is approximately equal to 80 kilograms. And I'll assume that the mass of number 2, Rachel, is equal to about 60 kilograms. Now, the other piece of information we need to know is how far apart they are from one another. So let's see, what kind of symbol could we use for that? D, we could use D for distance. What else? We could use X for separation along the x-axis. In this case, we're going to use R as the symbol that represents how far apart. So we can make a stick figure diagram out of this one. There they are. If we put Ross at the origin in our diagram, then we can measure outward. Instead of calling this the x-axis, we can call this the r-axis, or the radial axis. Let's make an assumption that the distance between them, well, let's just take the case where they're standing 5 meters apart. That's more than enough for proper social distancing. I'm going to make another vector along the radial line, but I'm going to make a vector that's exactly 1 unit long. So instead of 5 meters, I'm going to say that vector is 1 unit long. If so, then it's a special value we call r hat. If we put a hat on top of any vector, we refer to that as a unit vector. And all unit vectors have a length of 1. Okay, now here's the equation. We can find the force of attraction if we assume that gravity is an inverse squared law. There are a lot of inverse squared laws that you encounter in the study of physics. There's something known as Coulomb's law that finds the force of attraction between charged objects. There's another law called the law of Biot and Savart. Spell that one out. Biot, Savart. That's a law that describes the force of interaction between moving charges, and therefore gives us a way to calculate magnetic forces. Anyway, Newton's law of universal gravitation is an inverse squared law also. And the reason we use that phrase inverse squared law is because the force is inversely proportional to the distance between the two objects, m number 1 and m number 2. So the distance r is squared, and in the inverse, in the denominator of the equation, so it represents an inverse relationship. Now, if either of the masses gets larger or smaller, that influences the force. So if both Ross and Rachel went on crash diets, they'd be less attracted to each other. If we look at this dimensionally, it's not going to work out, because force should be measured in newtons, but on the right side of the equation, we would have kilograms times kilograms divided by square meters, and that's not a newton. So we can fix it if we include a constant of proportionality that has the correct units. So let's think about this. Try to come up with a guess at what these units would have to be. So we know this part of the equation altogether gives us kilograms squared over meters squared. So I'll just make a guess that whatever the units are for this constant capital G, they must have units of meters squared per kilogram squared, so that they'll cancel the other units in the equation. And then as long as that capital G also has built into it newtons, that's the only units that would be left when you multiply everything out. So that's it. This capital G is a quantity measured in newtons times meters squared over kilograms squared, and it's actually equal to a very small value. It's equal to 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. In another video lesson in this unit of study, we'll go over something known as the Cavendish experiment. So that's named after Henry Cavendish, who performed a famous experiment in order to determine what this constant is equal to. So now we have everything we need to determine what the attraction is between Ross and Rachel. The force is equal to 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared, multiplied by 80 kilograms, and multiplied by 60 kilograms, and then divided by 5 meters squared. Were we right about these units? Let's take a look at this one more time. A kilogram multiplied by a kilogram gives me a kilogram squared, but those square kilograms cancel with those. If these meters really do get squared, then they'll cancel with these meters squared. Yeah, we'll be left with newtons as the answer. Grab a calculator and see what you get. So I got a force of 1.3 times 10 to the negative 8th. That's tremendously small. And that's generally the case. The force of gravity is the weakest of all the fundamental forces in our universe. Recall all the fundamental forces: gravity, electromagnetism, strong nuclear force, and weak nuclear force. The weakest of all those forces is gravity, and the only time you have an appreciable numerical value when applying this equation is if at least one of the two masses is large enough to overcome this very small power of 10 built in to the universal gravitational constant. So maybe we should ask this question: if mass number 1 still represents Ross, but now mass number 2 represents the Earth, what's the force of attraction? And don't jump to a wrong conclusion here. Some people would say, well, if he's standing on the very surface of the Earth, then the distance between him and the Earth is 0. And if the force of gravity is expressed according to Newton's law of universal gravitation in this manner, if R is equal to 0, then the force approaches an infinite value. But R isn't really 0, is it? We don't measure from surface to surface, we measure from center to center. So the distance between Ross and the Earth is the distance from Ross's belly button to the Earth's belly button, so to speak. And that distance, for all practical purposes, is the radius of the Earth. Now, to remind you, the radius of the Earth is about 4,000 miles. That's the same thing as 6,400 kilometers, which could be written as 6.4 times 10 to the 6th meters. Do we really need to add on the additional 1 meter or so from Ross's feet to his belly button? Adding 1 more meter into this value, we won't even see it if we only stick to 2 sig figs. So, for all practical purposes, for anything that's at the surface of the Earth, its distance from the Earth, when using this equation, is the radius of the Earth. Okay, the mass of the Earth would also have to be known, right? Mass number 1 is still 80 kilograms. We know the value of G is 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. And now we know our distance, for all practical purposes, is just the radius of the Earth, 6.4 times 10 to the 6 meters. And don't forget, it's an inverse squared law. We're going to have to square that value. So what's the mass of object 2? What's the mass of the Earth? Well, the mass of the Earth is 5.97 times 10 to the 24th kilogram. That's a lot of kilograms. If you want, you can memorize that as 6 times 10 to the 24th kilograms and be close enough in all your answers that you can get away with it. So there we go. So calculate this all out and see what you get. Wait, before you grab your calculator, I'd actually like you to do it this way. Why don't you calculate what you get when you multiply g, 6.67 times 10 to the negative 11th, and then don't forget to square this value of r, so include that in your calculation, and then also factor in the mass of the Earth, get that part of the calculation, but leave out this part. Put everything into the formula except leave the mass number 1 out of it. Then the units won't come out in newtons because you'll have neglected these kilograms. So I guess you're going to get an answer, instead of an amount of force, you're going to get some number of newtons per kilogram. I want you to figure out what that value is, and then you'll have to multiply in the 80 kilograms that you neglected as the final step. So in other words, you'll have F equals m times some other value. Okay, grab a calculator, see what you get, multiply 6.67 times 10 to the negative 11th times 6 times 10 to the 24th, and then divide that by 6.4 times 10 to the 6th squared. Do you have your answer? Hopefully it's the same as mine. If you plug this all in correctly, you got 9.77, which we could round up to 9.8. Oh, well, we recognize that. That's the value of freefall acceleration, had we expressed it in meters per second squared instead of newtons per kilogram. But you probably remember that a newton is a kilogram meter per second squared. So if we divided a newton by a kilogram, we'd have a kilogram meter per second squared divided by a kilogram. Kilograms would cancel out, and we'd be left with meters per second squared. The point being, there's no distinction between units of newtons per kilogram and meters per second squared. They're identical. And so instead of thinking of g as acceleration due to gravity, let's change the language here and think of it as the Earth's gravitational field strength. So instead of meters per second squared, we'll think of g as some number of newtons per kilogram. Meaning if we put a 1 kilogram block at the surface of the Earth, then it would weigh 9.8 newtons. There'd be 9.8 newtons for 1 kilogram. If we put 2 kilograms at the surface of the Earth, then it would weigh 19.6 newtons. 3 kilograms, 29.4 newtons, and so on and so on. So it's not a coincidence that you got this value of 9.8 when you multiply g times the mass of the Earth and then divided by the radius of the Earth squared. That's exactly what you should get, and this is why Newton's law of universal gravitation has been shortcutted all semester long. We've just expressed it as F equals m times g, and we've just preloaded the work because we know the gravitational field, the gravitational constant is indeed a constant. The mass of the Earth is always the same value, and for any object at the surface of the Earth, the distance to the center is known. So why use this long form of the equation when we could find the force of gravitational attraction this way? Okay, so what we really need is an example in which the distance between an object and the Earth is not the radius of the Earth itself. So we could ask the question, what's the force of attraction between the Earth and the Moon? So you're going to need a few values for that one, and I've provided them down below. We already know the mass of the Earth is about 6 times 10 to the 24th kilograms, really 5.97 times 10 to the 24th. So here's a new value, the mass of the Moon, 7.35 times 10 to the 22nd kilogram. And by the way, if you want a sense of scale here, if you were to grab a basketball, hold that in one hand, and in the other hand, hold a baseball, that's about right when comparing the diameters or the sizes of the Earth compared to the Moon. The other quantity we're going to need is the distance between the two if we want to use Newton's law of gravitation to find the force of attraction between the Earth and the Moon. Oh. So did we ever figure out what's the force of attraction between Ross and the Earth? Well, since we already recognize that we can just use this shortcut, then all we have to do is multiply 80 kilograms times 9.8 newtons per kilogram. Might as well round that up to 10 to make life easy, and say the force of attraction between Ross and the Earth is approximately 800 newtons. Okay. So why can't we do the same thing for the Earth and the Moon? Why can't I just multiply the mass of the Moon times 9.8 newtons per kilogram? Because the Earth's gravitational field strength of 9.8 newtons per kilogram is only the value at the surface. If we were to go 1 Earth radius above the Earth, so at the surface of the Earth, the distance between any object and the center is 1 Earth radius. If you were to double that distance, so maybe we place a satellite or some other spacecraft at a distance of, well, in total now, 2 times the radius of the Earth, then the gravitational field strength you might think would be half as much, but wait a minute, this is an inverse squared law, so the Earth's gravitational field strength at this point is about 1/4 of 9.8, or in other words, about 2.5 newtons per kilogram. And if we were to go yet another Earth radius away, then we'd be at a total distance of 3 Earth radii, and so the gravitational field strength there isn't merely 1/3 of the value of the surface, it's 1/9 of the value of the surface gravitational field strength, which would give about 1.1 newtons per kilogram, and so on. Well, by the time we get 1, 2, 3 Earth radii away, are we close to the distance of the Moon? Turns out holding a basketball and a baseball in your hand is a good way to get a sense of the relative sizes of the Earth and the Moon, but your arms aren't long enough for you to properly display the distance between the Earth and the Moon. So from the center of the Earth to the center of the Moon, there's a distance we can call r subscript en, the separation between the Earth and the Moon. And that value, it turns out, is maybe more than you think. So here I'm presenting it as a question. How many Earths could you put end to end in between the actual Earth and the Moon? It turns out you can fit 30 Earths in between the Earth and the Moon, which means 60 times the radius of the Earth, right? The diameter of the Earth is 2 times the radius of the Earth, and if you can fit 30 Earths between the Earth and the Moon, then the Earth-Moon distance is 60 times the radius of the Earth. Well, if you use the value given here as the radius of the Earth, 6.4 times 10 to the 6th meters, if you multiply that times 60, you'll find that the distance from the center of the Earth to the center of the Moon is about 3.84 times 10 to the 8th meters. That corresponds to 384,000 kilometers, or about 239,000 miles. So the force of attraction between the Earth and the Moon is 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared, multiplied by the mass of the Earth, 6 times 10 to the 24th kilograms, multiplied by the mass of the Moon, 7.35 times 10 to the 22nd kilograms, divided by the distance between the two of them squared, which is 3.84 times 10 to the 8th meters, and don't forget to square that quantity. I think it's helpful for us to have this conversation about units one more time. Kilograms times kilograms gives us square kilograms, which cancel here. Meters get squared, so they cancel here, and all we're left with is newtons. Perfect. So grab your calculators one more time. So you get a force of 1.99 times 10 to the 20th newtons. That's a lot. Let's double check, see I didn't make any mistake. We could have made this a little easier. If you want to spare yourself some keystrokes on your calculator, you could just multiply out the numerical parts. So multiply 6.67 times 6 times 7.35 and divide that by 3.84 squared. And then do all the powers of 10 in your head, because powers of 10 are so easy to work with. So 10 to the negative 11th times 10 to the 24th times 10 to the 22nd divided by 10 to the 8th squared. Well, that would be 10 to the 16th, right? So 10 to the 24th and 10 to the 22nd can be combined as 10 to the 46th. 10 to the 46th and 10 to the negative 11th can be rewritten as 10 to the 35th, and 10 to the 35th divided by 10 to the 16th would give 10 to the 19th. And so we could then multiply the 6.67 times 6 times 7.35 and divide by 3.84 squared, and that's going to give us 19.9 times 10 to the 20th, and so we can borrow a power of 10 here. Call this 10 to the 20th and move that decimal over one place. Well, either way, we find that it's an extremely large amount of force, but then again, it's being applied to a very large amount of mass. So let's figure out what the acceleration is for the moon. Newton's second law of motion says acceleration is force divided by mass. So if we take a force of 1.99 times 10 to the 20th newtons and divide it by a mass of 7.35 times 10 to the 22nd kilograms, we don't get a very large acceleration. 1.99 times 10 to the 20th divided by 7.35 times 10 to the 22nd gives an acceleration of 0.0027 meters per second squared. Now, exactly what type of acceleration does the moon have? Is it really slowly accelerating toward the Earth? If it does, it's going to move into a position where the gravitational field is stronger, and then that acceleration would actually, it wouldn't be constant, it would increase, and the moon would accelerate even more. And this has been going on since before man ever populated the Earth, so how come the moon hasn't crashed into the Earth? Well, the moon is not stationary relative to the Earth. Sorry, this figure's not drawn to scale. I'll never be able to properly show you on the page the right distance between the Earth and the moon. Remember, it should be 60 times the radius of the Earth. So I just have to shrink that distance so that both of them appear on the page. Note, the moon is orbiting in nearly a circular orbit around the Earth. Later in this unit, we'll talk about elliptical orbits. But the moon has a velocity, and that velocity vector is tangent to its circular orbit. So we'll call this v subscript t for tangential velocity. So the law of inertia says the moon would like nothing more than to keep going along this straight line path. But there's a force of gravity pulling in toward the center of the Earth. Remember what we call forces that pull toward the center of a circle, we say that's a centripetal force. So if we found an acceleration by dividing a centripetal force of 1.99 times 10 to the 20th newtons by the mass of the moon, then we've really calculated a centripetal acceleration. And centripetal accelerations don't change the speed of an object, they just make a vector change direction. So instead of the moon following the straight line path, this inward pull of gravity causes the moon to change course a little bit, and now its velocity vector stays the same length, but it's moved off of this straight line path, and a little later in time, the tangential velocity points here, and all that happens is the speed stays the same, but the direction keeps changing. And all the while, the angle between the force and the velocity vector is 90 degrees. So the Earth does no work on the moon. It doesn't change its kinetic energy and it doesn't change its speed. It just changes its direction. And so we have a centripetal acceleration of 0.0027 meters per second squared for the moon. Okay, I have a picture here of the International Space Station, and in the opening video for this unit of study, you saw an astronaut on board the ISS, and at one point she squeezed a blob of water out of a container and was able to sip it out of midair. So it might have appeared that everything on board the space station was weightless. So let's talk about apparent weightlessness. We have to use the word apparent because, as I stated at the opening of this video, I think I said this one, that the International Space Station doesn't really orbit that high above the surface of the Earth. So once again, the scaling here, the radius of the Earth is about 4,000 miles, or 6.4 times 10 to the 6th meters, and the International Space Station, just like the moon, orbits in a circle. It's just not as far away as the moon. In fact, it's definitely not 60 times the radius of the Earth from the Earth. It's only, I think it's less than 200 miles, which means it actually orbits within the atmosphere, but the atmosphere is so thin that it doesn't produce any drag effect. So that would correspond to, let's see, we did 4,200 divided by 4,000, so we can take a ratio of the orbital radius, lowercase r, to the planetary radius, capital R, then that's equal to a factor of 1.05, which means the gravitational field strength for the ISS in orbit would be less than the gravitational field at the surface. And it would be less by an amount equal to not just 1 over 1.05, but rather 1 over 1.05 squared. It's an inverse squared law. So the gravitational field strength at the position of the ISS is the inverse of 1.05 quantity squared multiplied by 9.8. which is equal to 8.89 newtons per kilogram instead of 9.8 newtons per kilogram. So a little blob of water has a force of attraction with the Earth, and let's say this blob of water has a mass of 100 grams. That's the same thing as 0.1 kilograms. So its force is 0.1 kilograms times 8.89 newtons per kilogram. And then the astronaut maybe has a mass of 60 kilograms. So the force of attraction with the Earth would be 60 kilograms times 8.89 newtons per kilogram. So which has a bigger force of attraction with the Earth? A little blob of water floating inside the space station, or an astronaut floating inside the space station? The Earth is somewhere down here in this picture. So there's a force vector, there's another force vector. They're clearly not the same amount of force. 0.1 times 8.89 gives us 0.889 newtons. 60 times 8.89 gives us about 533 newtons. So they're definitely not weightless. This is the weight of the blob of water, and this is the weight of the astronaut. And by the way, if the astronaut was at the surface of the Earth, her weight would be something more like 600 newtons instead of 533. So astronauts don't weigh that much less in the ISS than they do at the surface of the Earth, but they have an apparent weightlessness. And the reason is, if we want to find their centripetal acceleration, we would divide this centripetal force by their mass. But if I were to divide by mass on both of these, then it would just give me back the gravitational field strength. And keep in mind the gravitational field strength, although expressed in newtons per kilogram, would be the same thing as some number of meters per second squared, meaning that everything on board the International Space Station, including the space station itself, all have the exact same acceleration as one another. They're all accelerating at 8.89 meters per second squared centripetally. And whenever you share the same acceleration as your surroundings, you lose contact with your surroundings, and so you have an apparent sense of weightlessness. So that's a fairly long introduction to Newton's law of universal gravitation. So for now, I hope you can relate to this mathematical expression. I would like it if you can commit to memory some important masses, like the mass of the Earth, and some special distances, like the Earth-Moon distance or the radius of the Earth itself. We'll move on in the rest of this unit of study and investigate the motion of the planets, and we'll even get into the motion of objects that move in elliptical paths, not just circular paths due to a force of gravity. So thanks for watching, and stay